Okay, I want to talk a little bit about the difference between a two-sample procedure and a matched pairs procedure. And first, the big thing is how the data is collected. That's kind of the key to decide on how you're dealing with a matched pairs versus a two-sample. And here are two sets of data, or four sets of data, depending on how you count it. But we are interested in exploring whether the weather can affect the number of calls handled by an operator during an 8-hour shift. And so we recorded the data in two different ways. There's two different ways we can collect the data. One is we take, here on the left, where we take individuals and we on randomly chosen days or randomly chosen sunny day, we record how many calls that they handle. And then on a randomly chosen rainy day, we record how many calls that they handle. Or another way to do it would be to have two different groups. Have a group 1 and a group 2. And in group 1, we have a group of individuals, and we measure how many calls they make on a sunny day versus how many that they make on a rainy day. And it's a different group of individuals. So with a matched pairs, what I've got is that this 50 is related to this 49 in that they're both Mike's responses. And, with a matched pairs, we're comparing how does the weather affect Mike versus how does the weather affect Greg. Does it make a difference depending on which person you're looking at in there? As opposed to here, you're comparing like Mike and Shirley or Peter and Chris. How do those two different individuals compare? We're going to get better results if we can do a matched pairs result, but it typically takes more time to do that, to actually carry out the experiment or to gather the data in there, because you have to gather that data from that individual twice in the two different situations. So let's start with the matched pairs, the matched pairs hypothesis test. And that's what we're going to start with. Is the first step, of course, is to talk about our hypotheses. We want to start with our null hypothesis. And our null hypothesis is typically that the mean difference would be 0. What I want to do is I want to look at the difference between, for each individual, how do they handle a sunny day versus a rainy day. So if I do like sunny minus rainy, I'm going to get 1 here on this one. If I do 51 minus 58, I'm going to get -7. 46 minus 55 is -9, and so on. And what I want to do is I want to do that subtraction for each individual value first. And what I'm saying is that if there's no difference between these two, then some will be positive, some will be negative, but it will average out to be 0. And that's what our null hypothesis is that there's no difference between the weather is unrelated to the two. And for my alternative hypothesis, I'm looking at something. I don't see anything in my statement about it being handling more calls or less calls, so I think this is a two-sided. There's nothing saying one weather is better than the other weather in terms of answering phone calls. So I'm going to make that a does not equal type of inequality there. So we'll work those as the null and alternative hypothesis. What I next need to do is I want to find my summary statistics for those. And I'm going to jump over to Excel and I'm going to look at this differences here. Let's see, where is my Excel? Too many things. There's my Excel. Okay, and what I want to do is I want to create those differences in there. So I'm just going to take the sunny day and subtract the rainy day and find that for the whole way down. And that's actually the data I want to work with. Come on, copy all the way down. One more. Okay, well, I got one too many in there, but I'll just delete that there. And let's call this the difference in there. We'll label that column. And so our null hypothesis is that the average of these should be 0. The alternative hypothesis is that they're not 0 that we're looking at there. All right, and I'm going to save that. I think I've got it saved as a CVS. Yeah. Yes, I got it saved as a comma CSV, comma delimited script, because I'm going to do this in Excel. Not in Excel. I'm going to do this in RStudio, just because it's got some great graphing capabilities in there. So let me jump over to RStudio. There's RStudio, and I want to import a data set. And I'm going to choose this first option here, and it is in my R scripts is where I saved that. And this was data sample 1, and I think this one is the .cvs file. Yep, that's it. I do have headings on there, and it's comma separated. That's exactly what I need there. And then I have to use the tab to get down to, I get to the import button to import that information. And there we've got it in there. All right. And what I want to do then is find the summary statistics and maybe make a histogram of that. And I've got a script that I created to do that. So let me open back in my R scripts here. I have a histogram and box plot. That should be the one to work with. And that uploads my my sheet. And so what I need to do is I need to start off by creating the renaming the data. And so this was the name of my file was 2sample1, and it might not like that. And the variable I'm looking at is the diff. Did I have 2 F's in there? I think I had 2sample difference as the value there. So let's run that script. Oh, it doesn't like the 2sample. It doesn't like the 2 at the start of it. Shoot. Okay. Let me go rename my file here really quick then. Save as in the current folder. And it doesn't like the 2 at the front. Well, that's news to me. We'll call it just sample 1. Comma delimited. Yes, I know. Okay. And back to RStudio. And I gotta import the data set again. Sample 1 was the one that we renamed it. Automatic, comma, yes, we have headings on there. And get to the import button. There's the import button. Okay, now let's go back to our script. And it's sample 1 and diff, I think, is what I want to do. And I'm going to rename it as the set radon, just because that's what the last script I did was doing something with radon. And if I hit the run, it'll tell us what the mean was. My mean down here was -6. If I calculate my summary statistics, it'll give me my quartiles there. I also need the standard deviation. Yep, there we are, STDEV. So let's run that script line, and I get S is equal to 3.7749. We'll keep that many digits. And if we make a histogram of that, we'll run that script here. All right, looks fairly normal. There might be one outlier here, but it's not too bad. And let's look at our box plot. What does the box plot look like? All right, our box plot looks pretty good as well. Yeah, we'll zoom in on it there. It looks pretty decent. Fairly roughly symmetric, kind of a small set of data. but we're going to assume that it's okay to go ahead and do a t-test on that. All right, so there I've got my data. I'm going to write down these numbers that I have up here. The mean was -6, and the standard deviation was 3.7749. And did it tell me my sample size anywhere? I think there's 9 values. Looking over here at the right, I'm pretty sure that there's 9 different values there on that. So I'm going to need that as well. So I've got x bar is equal to -6, s is equal to 3.7749, and n is equal to 9. And so then I'm ready to go do just a t-test on that. What I'm going to do is find my t-statistics. That's not the place I want to be. Let's go back to here. I found that x bar was equal to -6. S is equal to 3.7749, and n equals 9. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, I got 9 pieces of data there. So I'm going to calculate my t-statistic. It's x bar minus mu divided by s over the square root of n. So in this case, it would be -6 minus 0 over this 3.7749 over the square root of 9. All right, and let's go ahead and plug that into our calculator. So the top is going to be -6. I guess I can put in subtract 0, but I know what the answer is going to be. I don't really need to do that, but I'm going to put it there anyway. Divided by, and then our denominator does need to be in a set of parentheses, 3.7749 divided by the square root of 9. Of course, I could just type in 3 since the square root of 9 is 3, but I'm going to type it in as the square root of 9. And I get a t-statistic here of -4.768. All right, and what I need to do is then convert that to a p-value. So because I've got a negative value, I know that my sample mean turned out to be below the population standard deviation, or the population mean. And so I've got a lower tail value, but because it's two-tail, I want to look at both sides. So I'm going to do TCDF. I'm going to go to the distributions. It's up above the variables button there. It's a blue one. You got to push the second function to get there. TCDF, I want to go from -infinity. And it's always good to use a lot of 9s on -infinity for a t distribution because it has more area out in the tails in there. That's maybe too many there, but that's all right. And then I'm going to use my t value that I calculated before. I'm going to just use the previous answer button on my calculator to pull that up. And then the last thing you need is the number of degrees of freedom. And in this case, with a sample size of 9, I have 8 degrees of freedom. And so I get a p-value here of 7 times 10 to the -4. The calculator has shifted into scientific notation with the -4 over there. And so what that really means is 0.0007. You got to move the decimal place 4 places to the left to write that as a regular number. Oh, whoops, but this is a two-tail. Two-tail means I have to multiply that by 2. We're saying that it could be larger or it could be smaller, so you want to look at the probability of being as far away as we were, either 4.76 standard deviations below the mean or 4.76 standard deviations above the mean. So the t-distribution is nice and symmetric. We can just take our p-value and multiply it by 2. And so our p-value is actually 0.0014. And so let me go back to my OneNote here, and my t-statistic, just to be complete, worked out to be -4.768, and the p-value I found by doing TCDF from negative infinity, and so just put in a bunch of 9s there, to negative 4.768 with 8 degrees of freedom. But I got to multiply that by 2 because it's a two-tail value, and that gives me 0.0014 as my p-value. So that's probability is pretty small, and so we would say you probably want to reject the null hypothesis here. And say that the weather seems to, our sample suggests that weather does make a difference. In the number of calls. All right, so overall, for the entire population, it would seem that the weather does make a difference. And we can say that at certainly at the 5% significance level, even the 1% significance level, based on our data that we had there. All right, let's go do a two-sample test. So if I wanted to do a two-sample test, so if my data I thought was, if I look at the second set of data where I have two different individuals in there, it's different groups, so that this 50 is Mike's score and this 49 is Shirley's score. Mike and Shirley, you know, I don't know how they're related. They're probably not the same individual. There's no reason to really associate those two. And that becomes a two-sample thing. And so I'm going to make some sort of claim that like mu1 is the same as mu2. What I'm going to do is look at these two samples, that the mean of my first sample, the mean number of calls on a sunny day for our entire population, is the same as the mean number of samples on a rainy day. That would be mu1 equals mu2. Or you might see it as mu1 minus mu2 equals 0. When we want it to have that equals a number, a lot of times we'll write it that way. And our alternative hypothesis, mu1 minus mu2 is not equal to 0. Or mu1 doesn't equal mu2. We're saying that there's a difference between the two. We like to compare it with 0 there to say that there's some sort of mean in there. All right, I need to double check my sample statistics again. So let me go back to, I need to go in and I need to, there's my two sample data that we're looking at. I do need to change the name. I have that number at the front and it's not going to like that in there at all. So I'm going to, again, save this as a CSV, comma separated value sheet, and I can't start with the number 2, I guess, in seems to be giving us problems in RStudio. So let's just call this sample 2 and hit the save. And yes, I know it's gonna not like that, but that's okay. It's gonna give me that extra warning. All right, RStudio, here we come. I need to import this data set. And it's in my R scripts is where I saved that. There's sample 2. And comma separated. Yep, that all looks good. And we've got our names there. And we've got a heading row. Whoops, got a row of headings. I need to change that to yes. And there's the import button. So I can pull that value in. All right, and I need to open up the appropriate script there. So rather than memorizing all those commands, I can just go in and open up my script, and I'm looking at a side-by-side box plot is probably what I want to do. All right, and my data is in sample 2 is where my data lives. Is now in sample 2. So let's run that. Oh, capital S. That's why it's saying object not found. And this shows us the first bits of our data. And what we need to do is we're dealing with sorted data down here. We're looking at this second column. And so we want to do data sunny and data rainy as our values. Our main category will be like calls answered. Our X label will be weather. And the Y label will be, well, calls. Let me call this weather and calls. And let's look at that. Let's see how well that runs. What did you not like? Oh, there it is. It generated my graph over here. Let's zoom in or zoom out to look at that. And oh, it looks like there's definitely a difference in the means between the two. Certainly one group has a mean that's much higher than the other one, or at least the median appears to be considerably higher. And in fact, it looks like 75% of these scores are above even the highest score on that one. Looks like I might have one outlier in that second set. But you know what? I'm going to go ahead and run my t-test. Again, it's a small set of data. And there might be an outlier here in this second set of data, but let's go ahead and do that. So I wish I had sunny and rainy and sunny down here at the bottom, so that would be something to kind of try to tweak in my labeling to see if I could get that to ever come up down there, but we're going to leave it like that. I do need to find my summary statistics on that, and so let me just sit back over here to my one sample one. It was mean was the command that we use, so let's try mean over here. There we are, mean, and then in parentheses it was data sunny. Let's see if that works. Okay, it gave me a value down there, 50.22. And if I do standard deviation, data, $, sunny. So the command call for that is you have to call it your name and then which column you're looking at there. I'm getting a standard deviation of the sunny data of 2.108185. And if I do mean of rainy, I'm just going to go up here and change this. And so I do those. The mean of the rainy days was 56.333, and the standard deviation of the rainy days was 3.391165. Okay, so those are my values. I want to go ahead and do my t-test on that. So should we go to the calculator next? or yeah, let's go ahead and let's go to OneNote just to make sure that we've written down that what we've got there. So we've got two sets of data. I've got X bar for the sunny days was 50.222. So X1 I'm going to call the sunny days. And my standard deviation for the sunny days was 2.108185. The mean for the rainy days was 56.3333, and the standard deviation of the rainy days was 3.391165. And so I want to calculate my t statistic. Well, the n on both of those, by the way, is 9. I have the same. It's actually the same set of data for both of those. It's just that it depends on how you gathered it and what groups that you're going to do. I'm going to calculate my t statistic. It's going to be x bar 1 minus x bar 2 divided by the standard deviation of your sampling distribution, which would be S1 squared over N1 plus S2 squared over N2. And that's going to give me my sample values. So let me crunch those into my calculator here. I want to do 50.222. That was an infinite number of 2's. We'll put in several there. Minus 56.333. And we'll try to do the same number of 3's. 1, 2, 3, 4, 5. Yep, same number of 3's. X bar 1 minus X bar 2 on the top. On the bottom, I need the square root of S1 squared, which was 2.108. Oops, got too many zeros in there. 8. 1. I'm going to round it to 9. That's squared divided by 9 plus 3.3911, and then it rounds to 7 squared divided by 9 and a parenthesis to close off that square root. And let me double check one more time, look over that. Yep, that looks like the correct thing to do. I'll hit the enter score key and I get a t-score here of negative 4.59. And then I want to do the p-value. I'm going to again go to tcdf. I want to go from negative infinity up to my answer. And my degrees of freedom would be the smaller of n1 minus 1 or n2 minus 1. In this case, 9 minus 1 is 8. Doesn't matter which one we're doing. It's going to be 8 there. And then this was a two-tail, so I have to multiply my p-value, my tcdf, by 2 to do that. And here I'm getting a p-value of 0.0018. 0.0018 for my p-value there. So again, another small p-value, so I would reject the null hypothesis. And this data also seems to suggest that the value, that weather does make a difference, and it seems like kind of seems like it makes a difference that on sunny days maybe people are more distracted thinking about what's going on outside. Oops, I forgot the and so maybe they're not answering as many calls. So I'm going to find my p-value here is 0.0018. 0.0018. It's a larger p-value than we got with the the matched pairs. It's 0.0014. Not a big difference, but it is a difference, and that's because matched pairs are generally a better test. If you can do a matched pairs, do a matched pairs. But again, it typically takes longer and it's more expensive than that there. So going to still have the same conclusion, and this video is getting awfully long, so I'm going to end it right there.